Welcome to 11th lecture of video course on tribology. The topic of this course is lubrication and lubricants. We have studied friction mechanisms and wear mechanisms. If both are harmful, if we don't desire friction, we don't desire wear. There may be another number of possible solutions, but one solution is a lubrication. If we provide lubrication, then wear will come down, will reduce, friction will reduce. That is why when we define lubrication, we say that lubrication is a process, is a mechanism to reduce friction and wear between relatively moving contacts or tribopair. And when we define lubricant, we say it is a substance which is interposed between two substances or two solid surfaces, so that shear strength of the interface is reduced, friction is reduced, subsequently wear is reduced. I want to give more emphasis on the wear decrease or reduction in wear rate compared to reduction in friction, as it was pointed in earlier lecture. Wear reduction is much more compared to friction reduction. Friction reduction can be 100 times, but wear reduction can be 10,000 times using proper lubrication mechanism. It is really very interesting, and we have number of application where the lubrication is required. You can see this picture is one of the very common example. It is a standard lock mechanism. We have key over here, there will be bolt connection having some geometry. Of course, it is not a true or threaded bolt, but we can say it is a bolt because it gets engaged in the door slot and locks the door. Here we can find if there is a on and off key, there will be this component or this bolt will be reciprocating. If there is a reciprocating motion, then friction will be there, and if we do not provide proper lubrication or we do not provide lubrication layer on that or proper coating on the surface, then there will be high friction and jamming action will occur. It will not work satisfactorily for a longer time. Similarly, there is another mechanism what we call as a window lifting mechanism. Window pan is generally lifted. If it is a power drive, then we use a gear mechanism, and generally gear mechanism in this case particularly it is a motor, small size motor is engaged with the complete gear, and a sector gear is moved with this spur gear or worm gear pair, whichever engagement is there. As there is again tribo surface, for satisfactory work, we will be requiring lubrication, either solid lubricant, liquid lubricant or semi-solid lubricant, so that it can function properly without much restriction or jumping mechanisms. So, another common example is a pendulum clock. We know the pendulum clock has a relative motion as well as a surface to surface contact. It requires a lubricant to work smoothly. If we do not provide lubricant, again it will not work, and it will consume more power compared to it is expected. The question comes, how lubrication really helps? It was earlier mentioned, it reduces the friction, it reduces the wear, but in addition to that, there are a couple of more advantages of lubrication. We said many times it reduces the failure possibility due to the sudden change in load, sudden change in lubrication condition, sudden change in misalignment. If there is some lubricant which is sticked to the surface, it will work satisfactorily for the fraction of second or transient time. In addition to that, we can say if there is a proper lubrication, it reduces the stress concentration. If there is an irregular surface, the irregular surface will be filled with the lubricant, and that will reduce unevenness, it will reduce stress concentration. Many times we know that stress concentration factor goes up to 1.7, 1.8. That means if you are providing a lubrication mechanism, we are going to get benefit around 40 to 50% on that. In last lecture, we studied about the cam failure mechanism or cam failure analysis, where the surface failure, surface fatigue was emphasized. If we provide a lubricant, that surface fatigue failure will reduce. It was also mentioned that if we provide a lubricant, the coefficient of friction will reduce, sliding will reduce, and that will reduce force required in tangential direction. If the force required in tangential direction is reduced, fatigue failure will reduce. Or we say that life will be slightly on higher side or maybe greatly on higher side, depend on the lubrication mechanism which we are providing. And this stress concentration factor, which is been emphasized, is common in number of devices like a transmission parts. If we provide a lubricant, if we do proper lubrication, transmission part stress concentration will reduce. Similarly, bearings, some micro pits are generated, or it's slightly irregular surface that can be reduced, stress concentration can be reduced. Similarly, cam follower mechanism, which has relative motion as well as a reciprocating motion, rotational as well as a reciprocating motion, that stress concentration factor will reduce in that. In addition, sometimes we require seal phases with a solid lubricant to give mechanical contact, but lubricate such the way the friction and wear is reduced. In that case, the solid lubrication is used. To compare lubrication mechanism with a solid mechanics, we can take this example. You can see that two surfaces, surface 1 and surface 2, subjected to tangential forces. If the surface 1 and surface 2 are subject to tangential force and they are interlinked, they are linked one way or another way, then there will be some sort of shear deformation. The shear deformation is generally given in angular way, that phi, or it can be linear term, the sigma delta x. If we want to represent in terms of stress, you can say that tau is equal to g into phi. Here g is a shear modulus. Shear modulus is generally given in terms of gigapascal. For most of the metal is a gigapascal. For polymers, it may turn out to be megapascal. But if the shear modulus is reduced, the shear stress is going to reduce for the same shear deformation. So, that is the advantages. And if I reduce this constant shear modulus to the eta, which is viscosity in this case, I am taking example of liquid and assuming the liquid is a non-Newtonian liquid. Then in that case, non-Newtonian liquid case, tau with the shear stress can be given as a viscosity into shear rate. The shear rate is expressed in terms of velocity gradient. Now, if I compare G versus eta, G is modulus of rigidity or shear modulus, expressed in terms of gigapascal for most of the materials, while eta is generally expressed in terms of millipascal second. It is almost a difference of 1000 or more. That means, whatever the shear stress generated in liquid will be lesser than 0.1% compared to the shear stress generated in solids. And we know if the shear stress generation is much lesser or shear resistance is much lesser, interface will glide, it will move smoothly, it will reduce coefficient of friction, and subsequently it will reduce the wear. In other words, whenever we are providing lubrication, adhesive wear is going to come to the almost zero value, or adhesive coefficient of friction will come down to the zero. I can't say for other mechanisms. For abrasive mechanism, yes, it will reduce, but not come to the zero level. Corrosion case, it will reduce friction as well as wear will reduce, but not necessarily it comes to the zero. However, if we are providing a lubrication and proper lubrication, adhesive wear mechanism will come down to zero. Only the abrasive wear mechanism will work if there is no complete separation between solids. If there is a complete separation or lubricant is able to provide thick lubrication completely separating two surfaces, then in that case wear will be zero. That is required for most of the applications. We discuss here shear stress relation for Newtonian liquid, but if we think about the non-Newtonian liquid, we can say behavior may be expressed as a BB. This graph is a shear stress versus shear rate. This graph shows clearly the domination of the phi compared to tau. While there are liquid also which will show the behavior like CC curve, and there are few liquids or the semi solid, like an example of the grease. They will show behavior initially they will not deform at all if the shear force is applied, and once it is applied it will show a Newtonian behavior. Typically Bingham liquid, what we say use a term with the Bingham liquid behaves like that. There will not be any shear deformation initially, and once the shear deformation starts, then it will work as a Newtonian liquid. So, we treat this kind of the liquid as a semi solid liquid. It is showing a behavior like solid initially, and subsequently it is turning out to be liquid. So, we can say we can conclude from this slide, we say that presence of lubricant reduces the stress concentration factor. That is a substantial and it is a very good factor for us. A method of the replenishing the lubricant decide overall performance. It is not only the providing lubricant at one instant, it is a continuous phenomenon, and if lubricant is wiped out, is squeezed out, then we need to again and again bring the lubricant at the interface. So, that is important, and that is why the lubrication mechanism or study of lubrication mechanism is very essential. It is not only the first sight you provide a lubricant and you will say that lubricant will remain there forever. We know shear stress, lubricant reduces shear stress, but along with the shearing this lubricant also will be wiped out. Once it is wiped out, then again shear stress will increase, or more force will be required. So, that is why we require again and again to replenish the lubricant at the interface. That is important, that is why the lubrication mechanisms are important. We will take a few examples to understand what do we expect from a lubricant. Actually, we are going to spend some money on lubricant, and if you are studying lubrication mechanism and the way lubricant need to be replenished, then question comes, how much cost will be involved, will that be justified compared to without lubricant. So, we can believe that there will be some expectation, if we keep some expectation and lubricant is fulfilling those expectation, then cost may not matter that much. Let us take an example of IC engine, piston and ring lubrication mechanism. There is a cylinder liner, there are pistons, piston rings, and there is a piston. Now, we know the piston has to reciprocate for the compression, for the expansion, and there will be combustion gases towards the cylinder side, or where the fuel and air mixture is burnt and gives us spark, get the expansion stroke. And there are some lubrication holes, not necessarily always cylinder has to have a lubricating holes. There may be a number of other provisions. We can provide a lubrication through piston rod also. So, number of lubrication mechanisms, but for convenience we have just shown that lubricating holes are present in cylinder liners. When we are providing the lubricant, what are the requirements? We say that lubricant must form a film, liquid film, to separate the surfaces. That means piston should not touch the cylinder liner, or piston ring should not touch the cylinder liner. There will be solid contact, there will be high friction, and IC engine is primarily used for the power generation. If it generates some power, maybe say X unit, and we know because of the friction we are consuming power by 0.2, 0.3, 0.4 x, that means only net profit will be only 0.6 units or 0.7 x unit. So, that is not desirable. Lesser the friction, better the results, and due to for that reason we want to separate the metal contact as far as possible. If it is not possible, then we can think about the material which are showing very low coefficient of friction even in the absence of lubricant. So, first requirement from IC engine lubrication mechanism is that lubricant must form a film to separate the surfaces. Second is that forming and completely separating is a one issue, but it should adhere to the surface. It is more like oiliness, the way we apply oil on our hairs, so that they get separated and there is a thin lubricant layer on the hair. Similarly, we want a thin lubricant layer always to be on a metal surface, so that there should not be direct contact. There are two things where I am asking thinking about attachment of a thin lubricant layer as well as separation of the two metal surfaces. Two things are different. We will be discussing this in detail. And in addition to these two requirements, there is another additional requirement, is that this lubricant must neutralize the corrosive product which are produced due to the combustion process, or some gases which are produced, and when they get mixed with lubricant, they mix acids like chloric acid, that will create a corrosive environment and will corrode the parts or machine part or IC engine parts. So, we need to have a lubricant which neutralize this corrosive product, which bring them either they is more like a give a cage to the corrosive product. So, the corrosive products are not free and to disturb the other IC engine parts. And finally, comes it need to withstand high temperature. We know IC engine temperature, minimum temperature will be around 90 degree to 95 degree centigrade, and it can reach to the 150 or 160 degree centigrade. So, a lubricant need to sustain this high temperature without failure. It should fulfill the function without failure at high temperature. So, these are requirements. Should make a film attached firmly with the surface, neutralize the corrosive product or some similar kind of products which are going to harm IC engine, and should be able to show performance functionality at high temperature. Let us take another example. Is a simple journal bearing. Journal bearing, we say that one of the cheapest machine support. It is one of the economic machine support. It can be made in any workshop without much problem, and this bearing has a requirement of the wedge action. There should be always some eccentricity to support the load, but its eccentricity should not be equal to 1. It should not touch the surface of the bearing. Obviously, that shaft should not touch the surface of bearing. There should be always some thickness, and that thickness should be greater than surface roughnesses. It should not happen that the surface roughness and H are almost the same order. In that case, this bearing will not work nicely. In addition, this figure shows a pressure profile. I think if we do not provide the lubrication, what will happen? This shaft will come and collide, or maybe say in contact with the bearing surface, and that contact, because both are the this is a cylindrical piece, bearing is also cylindrical piece. So, when they come in touch without load, there will be only line contact. If you apply a load along with the relative velocity, it is going to subject to the contact stresses, the way we explored in cam follower mechanism. So, to avoid that, if you are providing a lubricant, you can see the pressure profile is generated. So, instead of the localized contact, localized stresses, very high value stresses, now stresses are getting distributed uniformly. So, instead of 5 degree or 10 degree contact, it is going more than 120 degree contact. Instead of 5 degree contact is 120 degree, the stress concentration is decreasing substantially, contact stresses are decreasing substantially. So, we can say there is almost absence of contact stresses. There may be possibility at the initial or some condition, some contact is possible, but 99% it can be avoided. And what is additional requirement from the lubricant? We say that it should support the shaft plus load. Shaft is a dead weight of the shaft, and whatever the other element imparting the load on the shaft or transmitting the load on the shaft, that should be supported by this bearing, this lubricant which is used for the bearing. In addition, there is one requirement, it should damp the vibration. So, it need to have a damping qualities, it need to have a damping properties. So, from this point of view, from bearing point of view, what we require from lubricant, it should support the load, that means it should make a thick firm lubrication without failure. There should not be any contact stresses, whatever the situation, and finally, it should be able to damp the vibration. We are not counting here the temperature aspect, as such, because that will depend on the application. If it is used in compressor, temperature will be different, but used in IC engine, temperature will be different. So, those temperature requirement will come along with applications, but in absolute sense or just from the bearing point of view, these requirements are sufficient. So, if your lubricant is able to satisfy this requirement, we will be happy. This is one of the common example of our human body joints. We say whenever there are two bones and the relative motion, the joint will be made, and that joint requires lubrication. And we use a lubricant here as a synovial fluid is a more like a process fluid, or this gives an opportunity that wherever the liquid is flowing, that can be utilized as a lubricant by just giving some additives or adding some substances to that. So, what is in this joint is a femur is shown, tibia is shown, and there is a synovial fluid in the space. If there is a squeezing action and the motion, relative motion, there is a possibility of this liquid coming out and going back in. So, that requires some property. We say that this liquid need to contain proteins. It is nowhere related to lubrication, but it requires proteins that stick to the cartilage layer, resulting in smooth slides. So, it requires proteins one way, and they are acting as also boundary additives to provide a smooth friction or smooth sliding, low friction. When we are talking about low friction, we are talking about the order of like a 0.01 coefficient of friction, that is substantially low, very low value. In addition to that, this cartilage cells should not get damaged. That is why this synovial fluid need to have minerals, so that it can nourish the cartilage cells. Finally, need to have pressure viscosity coefficient, substantial coefficient. What we are saying that when the pressure is increased, this liquid should get compressed. If the liquid is getting compressed, it can sustain more and more stresses, or its viscosity will increase, and if viscosity increases, load carrying capacity will increase. And we have experience by changing pressure from x unit to the 1000 x unit, viscosity also changes, maybe from x unit to 22 x units. Changing viscosity is essential, increase in viscosity is essential whenever there is a high contact or high load is applied, which is inducing high contact stresses. So, from this point of view, we can say if we are using lubrication mechanism for the bone joints, it requires proteins, it requires minerals, and need to have viscosity coefficient, which is allowing viscosity to increase with the pressure. And from these three examples, I can we have a more number of we have number of examples, but just for our purpose, we are using only 3 examples, so that we can initiate discussion on this. So that lubricant properties are specific to the application. Yes, they are related to the application. It is not like we can go ahead the generalized lubricant properties. Okay, you pick up any lubricant, you use anywhere, and you will get solution. It is nothing like that. You need to understand what is application, what are the requirements, and apply lubricant accordingly. For convenience, we can divide this lubrication mechanism in 2 broad categories, what we call as a thick lubrication and thin lubrication. These pictures or these sketches are clearly indicating these results. So, the solid surface 1, solid surface 2, almost equal thickness is a liquid lubricant also. You can say that there is a thickness of the solid, this thickness of solid, and there is a thick lubrication, completely separated, nowhere related. So, materials, whatever the material we choose for surface 1, surface 2, is not going to affect the results, at least at the tribology level, at least at the friction point of view, or from friction and wear point of view. However, there is another thin lubrication mechanism. What we are saying that there is a thin lubrication mechanism, the surface 1 and surface 2. There is a thin lubricant layer which is attached to the surface, good enough to separate those 2 surfaces, but not good enough to completely separate it. Surface or lubricant layer which is coming in this this configuration is able to reduce coefficient of friction and reduce the wear rate also, but there is a possibility of detachment and engagement of this lubricant layer, that will be dynamic process. this lubricant layer gets attached and detached also. It will be continuous because there is a sliding, and there is a need to be a mechanism which will again bring back the lubricant layer on the surface. So, this kind of mechanism will get disturbed if there is a change in the condition. If we are increasing the load, naturally this lubricant layer need to be changed, or material which is required that need to be changed. We are increasing temperature, there is a possibility of the fluidity of this lubricant layer that will wipe up or wipe out or squeeze out easily. So, it is very sensitive, this kind of lubrication mechanism is sensitive towards the operating condition, increase in a temperature, increase in a pressure, or hard asperities which are coming into contact that will disturb the lubrication mechanism. So, as far as possible we should avoid it, we should come to this solution. This is much more robust system. However, optimization says that lesser space is always preferable. We need to go ahead with the micron size components or nano size components. So, in that case we require this kind of mechanism. That is why we say that when we design a hard disk drive where the space is a major consideration, in that situation we need to reduce this lubricant thickness, maybe say order of 10 nanometer or 3 to 10 nanometer, much lesser than 10 nanometer. When we try to understand the thick and thin lubrication mechanism, we say that for thick lubrication mechanism we need to use a Reynolds theory. Reynolds somewhere in 1886 published one scientific research paper after getting very good experimental readings and explaining those readings. He mentioned that if we rotate shaft in one of the bearing surface, then there is a possibility of pressure generation, and based on that observation he could develop a complete scientific theory, explain the theory why it is happening, and we need to use that theory to explain the thick lubrication mechanism, what will be advisable for overall system design. If I go ahead with this theory, we say that thicker and thicker lubrication will not be very useful. If I keep on increasing the thickness of a lubricant, it will not be very advantageous to us. Lesser quantity is causing lesser friction. Of course, there is no wear. This is the mechanism where there will not be any wear, but there will be only friction. If we provide more and more lubricant, there will be more and more friction. So, to find out what should be the optimum value of lubricant thickness, we need to use Reynolds theory, we need to use this kind of solution. Coming to the thin lubrication mechanism, as I mentioned earlier, is very sensitive to the environmental condition. So, it is far complex, it requires a huge number of experiments to come up with any definite solution, and requires scientific studies at the nano or micro to nano level, and even the lesser than nano level. We talk about the angstrom level in this case. For convenience, we can relate all this lubrication mechanism with one parameter, it is called lambda or capital lambda, as it was mentioned in second lecture. This lambda is a ratio of film thickness by composite surface roughness. It is also known as specific film thickness parameter, and what we call a thin lubrication mechanism can be quoted if lambda is lesser than 1. We can say thick lubrication mechanism when the lambda is greater than 5, but there is a possibility intermediate stages, what we say the mixed lubrication and we say the elastro-hydrodynamic lubrication. In case of mixed lubrication, we use both the theories, boundary lubrication as well as a hydrodynamic theory. Coming to the elastro-hydrodynamic lubrication, we use hydrodynamic lubrication as well as elastic deformation, and we need to make sure that the surface roughness is not coming into picture. Otherwise, we need to analyze and find elastro-hydrodynamic lubrication mechanism is without asperative contacts. As previously it was mentioned that if there is a wear generation or particles coming from outside, then quite possible hydrodynamic lubrication mechanism may turn out to be a mixed lubrication mechanism because of the particle occupying the space, reducing the effective film thickness. That is why the from EHL will move to the mixed lubrication mechanism. So, we need to keep all the theories ready. Whenever the situation comes, we need to use that theory and a combination of theories, so that get the overall possible or better solution. Let us start with the boundary lubrication mechanism. We say that this term was coined by Sir Hardy somewhere in 1922. Interesting, this guy was a biologist, he was from a biology background. What he quoted, he said very thin adsorbed layers about 10 angstrom thick was sufficient to cause two glass surfaces to slide over one or each other one another. He was mentioning about the thickness 10 angstrom thickness, that is very low thickness, and he could prove that sliding is much smoother compared to without this thickness layer. An interesting thing is that it has been observed by a number of researchers that even this thin layer is able to separate contacting surfaces. There will not be any metal to metal contact even with a layer thickness up to 10 nanometer. Naturally, we are talking about the surface roughness, but above that we coat layer such a way, we coat boundary lubricant layer such a way that surface roughness is not directly coming into picture. Wherever surface touch, wherever the aspirity touches, it will not touch the other metal surface directly, it will be touching with a superficial layer, that will be boundary additive layer. What we are trying to convey something like that, assume that there is a green box, we say that substance 1 or surface 1, the red color box substance 1 or material 1 or surface 1, surface 2, and then there is a thin layer on the red color box. This thin yellow color is a boundary layer and shows clearly, there is clearly separating this red color from the green color. Same thing, we are depositing also a layer on the blue color, blue color layer on the green color layer. So, there is a possibility that two surfaces can be completely separated, but how? The question is always difficult, but these situations are required by and large for all the machine components. Almost every machine elements require this kind of layer if there is a relative motion of that component. We say engineering equipment such as steel gears, piston rings, metal working tools, we are talking about the steel surface, depends on one or more of these lubrication modes. Whatever the lubrication modes that we are talking about, the boundary lubrication itself has two modes, what we call a physical absorption and chemical absorption. So, whichever mode that is required for these kind of elements, machine elements, to prevent severe wear or high coefficient of friction. An extreme case, as I mentioned, adhesive wear, that extreme case is a seizure, and seizure should be avoided as far as possible. So, question is that how thin layer is able to separate surfaces? It is difficult to imagine. Thin layer, we are talking over less than 10 nanometer, and we are saying the surfaces are completely separated, even though surface roughness may be in micron level. To explain that, this figure indicates there is a surface 1, surface 2, irregular surface has also been shown, and it is having some sort of carpet. You can see the carpet, right. This carpet has polar end and non-polar end. These molecules, polar end is used for a molecular attraction, so that it makes some physical bond with the surfaces, and there is a tail that provides some sort of flexibility the way carpet provides, to provide the smoothness of walking. So, this carpet surface completely separate this floor surface, There are two carpets completely separating surfaces, and we talk if I take some expansion, obviously that is a detailed view of one of the sketch, obviously that one of the small portion, what we get from that. We say these are the polar molecules which are attaching to the surface, and there is a tail, and overall height is 2 nanometer. It is not more than that, it is just 2 nanometer. How these are made is generally made with fatty acids. Fatty acids, we have a number of fatty acids in our body. All animal fats have a fatty acids. So, that carboxyl group is there, and there is a alkali tail also, it is something like a methane. Okay. This tail is vertically up, separating, maybe say it is not allowing other surface to come in contact with this, and this polar end is always attaching this tail to the surface. I will say that this polar end is required as an intermediate link to connect tail with connect grass with the surface. I am assuming this as a grass, which grass is something which can be easily bent and it come back to the original shape. We walk on field, grass is always there on the floor, and when we walk, grass will bend down. When we move away, it will come back to its own shape. So, that is a grass. It works as a carpet and completely separates the surfaces. That is why many times we call this kind of additives or this kind of lubricants as oiliness additives. They have oiliness property, which is they have attachment property. It cannot be easily separated. It requires some force, some push force to separate the surface from separate the oil from the surface. Now, we say what are the characteristics which are required from this boundary lubricants or thin film lubricants. First foremost thing is that a long chain, a long tail. Longer the tail, better the results. Lesser will be the coefficient of friction. So, we carry long chain molecules with one active end group. When we are talking about the active one end group, is something like polar end. Polar end is always active. So, we require active group at the end of the chain, which can attach itself to a solid surface and bound to that surface. It does not get detached easily. That is what we really require. Now, additional requirement is that it should get dissolved in mineral oils or lubricating oils. If there is a lubricating oil, it should get mixed with boundary additives. If it is not able to get mixed properly, what will happen? This kind of polar ends or this kind of boundary additives, they will get separated. We do not want that. We want complete dissolvement of the additives in lubricating oil. And finally, another requirement comes of the temperature stability. You say that temperature stability is important. As temperature increases, there is a possibility of reduction in molecular attraction, and that reduction will cause a detachment of boundary additives from the surface. That should be reduced as low as possible. We should provide lubricant such a manner, lubricant additive such manner, it can withstand the temperature or operating temperature. This figure gives explanation of the first point. We say that there are polar ends, active group ends, they are connected with the surface, and there is a non-polar end. This is a tail, is a chain. Longer the chain, better the results, because longer the chain, it can easily bend. It does not require much force to bend. I can think about the cantilever beam. Lesser the length of cantilever beam, it will require more force to bend. If longer the length of cantilever beam, it will require lesser force to bend. So, that is why we want a lesser force to bend this layer within elastic element, and lesser coefficient of friction can be generated, or we say produced from the surface or at the surface. Now, when we are saying that it should attach itself, we are talking about the number of layers. There is a possibility of number of parallel layers on a surface. If number of layers are lesser, then what will happen after the some sliding cycles, it will wipe out, it will be getting removed. But at the more and more layers, then there is a possibility of robustness, there is a possibility of that substance can be utilized. But we are talking of this without carrier fluids, we are talking this kind of lubricant additive layer on the surface without any carrier fluid, which we talked over here. It should get dissolved in mineral oil or lubricating oil. If there is no mineral oil available, there is no lubricating oil available over there, and we are solely using the lubricant which will attach to the surface, we are not using any carrier fluid, in that case this number of layers will be important. But if we are using mineral oil or using some other lubricating oil as a carrier fluid, and we are using this boundary additive boundary lubricant as a additives, then this kind of problem will not come. One interesting question comes in our mind is that why boundary lubricants are required, because we are talking about the 10 nanometer, and in earlier studies we observed or we learned that every metal has some sort of oxide layer. Metal will never remain virgin, it will always form some oxide layer, either firmly attached to the surface or weakly attached to the surface. It can be wear out, or it can be fractured, or it may be porous. So, the question comes, why do we really require boundary lubricants when the metal surface is already covered with a natural protective layer of oxides? Yeah, we can answer easily, say that protective layer will work for the certain load condition, and then there will be transition temperature or transition load. After that, the layer will get fractured. If you want to increase the load carrying capacity of the surface without removal of the layer, then in that case we require boundary additives. Similarly, protective layer will get removed from the surface and the temperature increases, or temperature increases with some sort of impact, it will get fractured. In that case, we require again a chemical absorption layer on the surface. So, boundary additives are important, boundary lubricants are important, even though there is a protective layer of oxide, because oxide layer may be fractured with by some additional load. We want to increase the load carrying capacity of the surface, in that case we require boundary additives. If we are operating surfaces at the low load condition, then it may not, in that case it may not require boundary additives are not required, or boundary lubrication is not required, because oxide layer itself will work as a boundary lubrication mechanism. There are some results available from Sir Hardy's experiments. He did a number of experiments with a different molecular weight lubricant and the different length of the chain. What he says that longer hydrocarbon chain, more effective separation between solid surface, and that will allow or bring a low coefficient of friction. These are the experimental results from Sir Hardy's experiment. We say that as the molecular weight is increasing, coefficient of friction is decreasing. It is not only for the boundary case, it may be also with a normal paraffin oils also, or normal mineral oil also, but reduction with a boundary lubricant is much more significant. You can see that this curve has a lesser slope, this has a more slope over here. Right. For same case, maybe say for 180 molecular weight, this coefficient of friction is roughly 0.18, 0.117, while this coefficient of friction is roughly 0.55. So, significantly high coefficient of friction. That means, boundary lubricants are always going to reduce coefficient of friction. There is another experiment, we say that this kind of lubricant also depends what kind of material is used. Is something, if you use a bismuth, coefficient of friction will be lesser. If I use a phosphorus bonds, in that case additives will not give that significantly good results. They have their different chemical structure, and bonding to that phosphorus bronze may not be as good as a bonding between the bismuth and additives. Similarly, for the steel surface it shows that, but in all the cases, so we are saying the linear profile as molecular weight increases, coefficient of friction is coming down, but attachment of individual layer depends on the material which we are using. We can understand some mechanism of boundary lubrication. So, that there are two major categories or classification. First is a physical absorption. It happens in almost all kind of mineral oils which have some sort of boundary additives, and particularly is important under the mild sliding conditions. But we are saying the mild sliding condition because a high sliding condition, high shear stress will be generated and will separate the boundary additives from the surface. So, will be this kind of situation will be good if there is a mild conditions and low temperature condition also. If the temperature is low, then in that case this will show the better performance, or physical absorption will be sufficient. What we are talking about physical absorption is something like a van der Waals forces. The molecules are getting attached to the surface by just physical interaction. There is no change in chemical structure, there is no deformation on the surface, it is just a sheer electrostatic force connection. While there is another category or classification which can sustain very high load and can see the severe operating condition also, that is called a chemical absorption. Chemical absorption, we can say there is a possibility of diffusion of the lubricant in the metal surface itself. It is more like making a firm joint, and the bond energy in that kind of joint is almost a 40 kilojoule per mole, which is substantially high. When you want to break this kind of joint, you need to give a lot of heat or a lot of tangential force to separate the layer. It is more like attaching to the surface firmly, making a layer which is completely attached to the surface. And additional thing is that in this case structure is also closely packed. Physical absorption structure may not be very closely packed, few sites will be empty where there is no lubricant, and while in the case of the chemical one, the structure is very compact, size will not be free, and there will be a factor reduction in coefficient of friction, and that is why it can see also severe operating conditions. We say that best solution will be combining physical absorption and chemical absorption together. That will be important. It have physical interaction as well as a chemical interaction. In that case, overall we will be getting good results. And almost in all lubricants which are marketed, they contain both the additives together. Some additives related to the physical absorption, some additives related to the chemical absorption. So, the low temperature, low sliding condition, physical absorption lubricant will work. Wherever there is a high temperature, a high load condition, this chemical absorption material will work or additives will work. The only drawback in chemical absorption is they are going to corrode the surface. So, when we study the corrosive wear, that time I pointed out this. Mild corrosion is going to produce a protective layer for us, that should be encouraged, and lubricant experts have understood that, and they made utilize this kind of concept to corrode the surface one way or another way, make a thin layer, but thickness should be such a low value, it should not get too porous, and fracture toughness should be also higher side. So, that way they are corroding the surface, but trying to keep the corrosion within a control. It should not be going beyond the control, it should not start damaging the surface. That is why we say that whenever we try to use a lubricant, it should be studied properly. It should not happen that by now that chemical absorption is a good event, it can sustain high temperature, high load. Okay, we mix 5%, you mix 10%, you mix 15% of this kind of additives. If we keep on increasing the percentage of additives, it may be much more harmful compared to not using that kind of lubricant additives. And we can say that this kind of boundary lubrication mechanisms can be controlled by adding additives in oil, which I explained earlier. Coming back to the physical absorption, we say that
These are also known as Arrhenius additives. They are attached with the surface due to electrostatic dipole force, and that is shown over here. This is the polar end, and we are showing physically they are not separated, just to show there is some field. This is the electrostatic field, there is a molecular attraction. We know electrostatic force is not very strong force, it is a relatively weak force, but it works for the mild operating conditions. Another point has been written on the slide is that these molecules get absorbed, may get attached as well as detached from the surface without any irreversible changes. Irreversible changes is something like will not change, will not damage the surface. It can be detached, it can be attached without damage to the surface. It is a dynamic process, and if you are using a lubricant which has a tendency to absorb these lubricant additives, that is required. If we do not use that kind of properties, lubricant additives will not get mixed with the lubricant at all. So, that is why we require a property, the lubricant, mineral oils or any other lubricant which we are using should absorb this kind of lubricant additives, but in addition to that we want this additives to get deposited on surface. That is why we say that it is a dynamic process, attachment and detachment will be a continuous process. And finally, it depends equilibrium constant, it depends on equilibrium constant, and equilibrium constant will depend what kind of concentration you are providing. If you are providing high concentration, more and more additives will go and deposit on the surface. If you are providing a lesser concentration, then it will lesser number of molecules will go and get deposited on surface. Coefficient of friction will change accordingly. So, there is a table which shows that percentage of boundary additives. Oleic acid is one of the fatty acid and is used as boundary additives. We say that if I am using carrier fluid as a mineral oil and 100% mineral oil, coefficient of friction is coming something like a 0.36. I am just taking a typical example. When we mix 2% of oleic acid in mineral oil, it is a proper mixing, it is nothing like just mix and leave it, it is a proper mixing, and the coefficient of friction comes down from 0.36 to 0.249, is roughly 0.25. Now, if we keep on increasing the fatty acid percentage from 2 to 10%, 5 times increase, the coefficient of friction is not decreasing that substantially. It is going down from 0.25 to 0.2. This decrease is not that substantial as we are increasing the percentage. Now, if you keep on increasing from 10 to 50%, coefficient of friction is not changing at all, it remains same. And 100% oleic acid, this is very thick, difficult to pump, difficult to flow it, and even in that case coefficient of friction is not decreasing significantly, it is coming roughly 0.2 on it. So, what we are trying to convey is that effective percentage should be utilized, it should not that we keep on increasing the percentage. I talked earlier for the chemical absorption, that will be harmful, even for the physical absorption, because oleic acid is a costlier compared to mineral oil. If I keep on adding this kind of additives, the overall cost of the lubricant will increase, which is not desired by number of customers. Now, what it says in addition to this kind of process is removal and attachment with the surface is generally encouraged by the dilute concentration. If the concentration is low, then there will be frequent engagement and disengagement of the lubricant additives from with the surface. However, if the concentration is increasing, there is a lesser possibility of getting detached from the surface. And often we give this kind of equation, we say that solute, the mineral oil plus lubricant additives, we are assuming it has some sort of A1 molecules and empty site. Whatever the surface has empty sites which can be occupied by lubricant additives is something like A2. Finally, only the adsorbed sites are equal to A3, which are really absorbing. It is nothing like every site will be occupied, and equilibrium constant somewhere K comes somewhere in like depends on the percentage, how much percentage we are depends on the adsorbed site. If we are increasing the concentration, then theta also will increase, right. So, the equilibrium constant will change, that can be used in the Gibbs free energy. Gives free energy, we can say it is more like a potential energy of a surface of a material. That much energy is required to distort the surface, to move the surface or to change its position. So, gives energy, gives what is how much energy we require to change the position, and it shows clearly it depends on the temperature. If the temperature is increasing, this term will increase in the magnitude and is a subtraction, that means Gibbs energy will change, Gibbs energy will reduce, and means we require a lesser energy to disturb the equilibrium. Otherwise, if the temperature is reducing, we require more energy to disturb the equilibrium. In other words, temperature is bad option. Temperature is a bad option for the physical absorption. If temperature is increasing, we need to see physical absorption will not be effective. Either we should increase the concentration or we should change from physical absorption to the chemical absorption. We will continue this topic in the next lecture, lecture 12th. Physical absorption will be continued and we will come to the chemical absorption. With this, I am ending this lecture. Thanks for your attention.